Good day, everybody. So it's my great pleasure to present to you Professor Fritz Gesztesy at Baylor University, USA. And he will speak, well, the title is on the screen. So please, thank you very much for accepting this invitation.
Thank you very much. Let me start by thanking all organizers, Alexey, Vladislav, Olga, and Tatiana, for their kind invitation to speak in this online seminar. As you can see from my title, I'm going to focus on the middle part of your uh, title of the seminar on differential equations. In fact, I'll focus on a very classical one, the Euler's differential equation, and on some perhaps surprising underlying special functions. So let's get started. This we will see soon again. So let me talk a little about the motivation. This is an offspring of investigations that we did, and I will say a little more about this soon, about essential self-adjointness of strongly singular homogeneous differential operators. And we had in particular looked at ODE examples on the half-line or PDE examples on Rn minus the origin. So the singularity will be at the origin. And you will see that we'll be looking at the nth order Euler differential equation, generalized hypergeometric functions, and most of all, Meyer's G function. So let me remind you of one way of presenting the nth order homogeneous Euler differential equation. And I have to admit, I'm using homogeneous in two different ways. So at the moment, homogeneous just means the right-hand side is 0, as opposed to the non-homogeneous version. But later on, I will look at differential expressions which are homogeneous with respect to x and not with respect to a right-hand side. So this is a little unfortunate, but it is what it is. Anyway, so the homogeneous Euler differential equation can be written in this form. The lambdas are complex parameters. There are n of them, capital N, and z at the moment is a complex variable. So you can say we are considering this differential equation in the complex domain. At the very end, if I still have time, I'm not entirely sure, I will look a little into these non-homogeneous versions, so where there is a right-hand side which is non-zero. Anyway, I wanted to point out, of course, a very nice picture of Euler that one easily finds on the internet. And on the right-hand side is actually his Basel home. And I mention that because my co-author in most of this, Markus Hunziker, is actually from Basel. So this is where Euler, the house where Euler was born. All right, so then let me do this manually. What I want to do in this talk is I want to focus on what looks like an eigenvalue differential equation. And I'm saying generalized here because it's not that I embed all this in an L2 space. No, I just look for this differential expression on y being a multiple of y. And so mu you could call the complex spectral parameter. But once again, I'm not embedding this in any way in an L2 setting. That's a different story. So where did this come from? Well, we were led to a study of this generalized eigenvalue differential equation because we were interested in essential self-adjointness properties in L2 of Rn in n dimensions of the following strongly singular homogeneous differential operator. And so now I'm using homogeneous with respect to x. So you see you have a power of the Laplacian, m is in n, and you add a strongly singular potential term if you want. And it's homogeneous, so this has dimension minus 2m, and of course this has dimension minus 2m. And as one can easily convince oneself, this is of course spherically symmetric, so you can do an angular momentum decomposition. And if you do that, you are led to special cases of this differential expression where the capital N is then an even number 2m. So we wanted to know essential self-adjointness properties of this object, and we were led to look at the eigenvalue differential equation you see in star. Okay, let me go to the next one. So here's a bit more about this. I have some references at the very end of the talk. So this is a paper with Markus Hunziker. We were interested in, again, essential self-adjointness of such differential operators, and the statement that one gets is this is essentially self-adjoint if and only if the following sequence of differential expressions, so you can see there's the mth power, this is second order, but now we are on the half line. So r is from 0 to infinity. So you originally start with L2 Rn dnx, but you end up with L2 on the half line with respect to Lebesgue measure dr. And the differential expressions are of this form. Okay. So using interesting results on the structure of zeros of polynomials, we were able to prove the following result. We have more of that, but since this is just motivation, I give you one. So suppose I do m equals 2, so the square of the Laplacian, and we add this homogeneous in x potential term mod x to the minus 4, then one can show that this is indeed essentially self-adjoint on that domain C0 infinity of Rn minus the origin, if and only if the constant C satisfies these inequalities, which you see you get different values whether n is between 2 and 5 or when n is larger or equal to 6. So in this particular case, I mentioned the angular momentum decomposition already. One is led to some special cases of tau 4. So you have 4 parameters here that are determined by C and by the angular momenta once you do the angular momentum decomposition. Now let me point out, this is a special case m equals 2, and we have a complete answer. We also have one for m equals 3. However, the situation, since higher and higher order polynomials and the zero structure of them is involved, this becomes rather delicate if m, so the power of the Laplacian, is larger or equal to 5. And I won't go into great details here, but let me mention one fact. So one is led naturally by looking at m equals 1, 2, and 3, that there should be a CMN real number, so that this operator is always essentially self-adjoint as long as the constant C is larger or equal to this constant CMN. It turns out this is wrong. So this is not true. We have a counterexample in 20 dimensions for m equals 5. It's a long story, so this would be another talk. But I just want to point out it can happen that you get islands of non-essential self-adjointness with respect to the parameter C. So what this means is, say, in the counterexample where m is 5 and n, the dimension, is 20, we have an interval from 0 to some number alpha, and then a gap, and then an interval from another number beta all the way to infinity. And so on 0 alpha and beta infinity, the operator defined on C0 infinity of r to the 20 minus the origin is essentially self-adjoint, but not on the non-trivial interval between alpha and beta. So there is an island of non-essential self-adjointness, figuratively speaking. Actually, this was one of the motivations. Another one has to do with the fact that we were interested in homogeneous ordinary differential expressions of this form. And of course, a situation like this leads to a special case of tau, where the underlying parameter capital N is even again, so 2n. All right. Now let's go towards Euler. So before we can do that, I need to remind you of the generalized hypergeometric function. So this is if you want a generalization of the exponential function. So for instance, if R is equal to S and all the alphas are equal to all the betas, then you just get the exponential function. So this is a well-studied object. You see this alpha L subscript K. So the subscript K, they denote the so-called Bochhammer symbol, which one can conveniently express in terms of a ratio of gamma functions. One thing that is important later on, and especially in our analysis, even though we won't see all the details in this talk, is that the function is very nice when it comes to the asymptotics, where zeta goes to 0. It actually starts with 1, so it's normalized. And I mean, that's immediately clear, of course, from this right-hand side here. Now, what's perhaps more interesting to us is it satisfies a certain hypergeometric differential equation of order S plus 1. So the S, once again, is the parameter you see here for the betas in the denominator. And here is the differential equation. So you can sort of see that there is a zeta d by d zeta without a parameter, or you could say that beta 0 was chosen to be 1 here. And then you have the alphas under this product. Anyway, this is the differential equation that this function FRS, so this generalized hypergeometric function, under the assumption that R is less or equal to S, satisfies. If one looks at it and analyzes it a bit, you see that zeta being 0 is a regular singularity, but zeta being infinity is an essential singularity of this differential equation. Now, let's make a few additional assumptions for the time being and look at some generic case where the difference of the betas is not an integer. Well, suppose we make this assumption. This is an additional assumption. Then one can actually see that the following S plus 1 functions, remember the differential equation was of order S plus 1, so if I want a fundamental system of solutions, I need S plus 1 functions. They can all be expressed in terms of generalized hypergeometric functions. So the first one, or the 0th one if you want, is just FRS, and S more of them, the M here runs between 1 and S, are other combinations of this FRS function. And with the exception of the first one, of course, there is a branch cut that's inherited from, in general, from this fractional power of zeta. Now, this is the generalized hypergeometric function. Let's turn to Meyer's G function. This is a complicated object in the following sense. It also depends on A's and B's, so the analog of alpha and beta that we had. But it's actually a contour integral. I'll say something about the contour in a minute. And you integrate certain ratios of gamma functions. So this is the object star. And here the contour begins and ends at plus infinity and encircles all poles of gamma of beta j, so of this term here, but once in negative orientation, but none of the other poles that come from 1 minus ak plus omega. So let me just remind you that 1 over gamma, so what you see in the denominator here is of course an entire function, but it's the gamma itself that has poles at, gamma of z has poles at negative integers and including 0. All right, so this is a way of a Mellin-Barnes type integral representation for Meyer's G function, if you want. And once you do the residue calculation, so to speak, you get an absolutely convergent sum, and that defines the left-hand side, our Meyer's G function. So this depends on M, N, and P and Q, and you can see that there's a division between B and 1 minus B and 1 minus A and A. And so the division is indicated with semicolons here. And here's the parameter N, here's the parameter M, and altogether you have P A's and Q B's. All right, so if we take this for granted, you notice very quickly that if M is 0, so if you look at this object, you get nothing of interest. What's more interesting is that as long as P is less than Q, so these are the two lower indices, and the left one is strictly less than the right one, there is a differential equation of order Q, and Meyer's G function satisfies this differential equation. So this is a bit different from the differential equation that we had for F, but in any case, this is the expression. I call this 2 star, and I might have to refer to it from time to time. We will have soon another differential equation 3 star, which we will use repeatedly. For that one, we will put N and P equal to 0. So the special case where P equals N equals 0 will play a large role when we specialize to the Euler differential equation. And once again, one can analyze this differential equation and see that the origin is a regular singularity, but infinity is an essential singularity. So let's talk a little more about Meyer's G function. So again, I'm in the generic case. So this means that my difference of b's is not an integer. And in that case, I can look at the g's and express them in terms of f's. And this combination that you see where j goes from 1 to q is actually a fundamental system of solutions of the Meyer G function differential equation 2 star that we just had here. Okay. If P is strictly less than Q, then this is of order Q, so you need Q linearly independent solutions. And one can see by looking at the asymptotics, one can quickly see that these are linearly independent functions. The f always starts with 1 near the origin, so these are linearly independent functions of the Meyer G function differential equation. But notice once again, we are looking at the generic case. So the difference of the b's are not supposed to be integers. So of course, that begs the question what happens in the non-generic case. But let me, just before we move to that, again, by looking at this expression here, state that the individual f's times this power zeta to the bj is of course also a fundamental system of solutions. So this is the generic case. Now, when you violate the generic case, so when some of your differences of b's are suddenly integers, this is sometimes called the resonant case, and then things get a lot more involved. So in order to take a closer look at that, I'm repeating the definition of the Meyer's G function. So again, this contour integral over ratios of gamma functions. And now let's assume that there is no interference with the poles in the numerator between these two gamma types of gamma functions, so b minus omega and 1 minus a plus omega. So this means from this point on, we will assume that a minus b is not a positive integer. The generic case I discussed earlier was that the difference of the b's was not an integer. And if you break this condition, then one can convince oneself that we get higher order poles on the right-hand side under the integral for Meyer's G function, and life gets complicated very fast. So let me now simplify the situation. I will not talk about the most general case. That's almost impossible in a talk. So what I will do is, as I promised you, I will look at a special case where n equals p equals 0. So where these two objects are equal to 0. I do this because that is related to Euler's differential equation, and especially this generalized eigenvalue Euler differential equation. And so we'll stick with that case from now on. I will not look at the general case any further. Now, if you make this assumption that p and n are equal to 0, then the G function differential equation simplifies considerably, and you get what I like to call 3 star, and I will have to refer to this at least 2 more times. And so this is now a simplified Meyer's G function differential equation. So let's look at the case where this generic condition is violated. So some of the differences of b's are actually integers. Well, then you have to do the following. You have to introduce congruence classes where the difference belongs to a particular integer. So between these congruence classes, you have the old condition that you do not have integers, but for these objects you allow that their difference now are integers. So let's first very quickly go back to the generic case. In this case, all these congruence classes consist of only one element. So this is when R equals Q. And in that case, we saw this before, that the fundamental system of solutions is of the form power times f's. Now our f's are somewhat special. There's a 0 here because we put p equals 0. And that since f has such a simple asymptotic as zeta goes to 0, you immediately get the asymptotic of this object is this power, fractional power in general, zeta to the bj times 1 plus order zeta. Here and later on, when I write 1 plus order zeta, I mean this is an analytic expression. So there's in fact, an entire expression. Now, this was the generic case, so we had seen that before. You can express that one entirely in terms of generalized hypergeometric functions, so you would not need the notion of a Meyer's G function to describe the generic case. But in the non-generic case, what you do next is you order the b's according to the real part with these inequalities. So in each of the congruence classes, you make an ordering. And if you do that, so this looks a little messy, I'm sorry, but it can't be helped. So what we're going to do is we're going to look at just one of the equivalent of the congruence classes, the first one. So let me go back quickly, and this would be this congruence class. The discussion of all of them is the same, so we may as well focus on just one of them. So this is what I'm doing here. So we are in the non-generic case. We look at one of these congruence classes, and one can then see that the simplified differential equation 3 star has the following linearly independent solution. So the first one is you see they have 0 for p and 0 for n. It's just a g, which actually in this particular case is just a power times a particular generalized hypergeometric function. So this is how it starts. The next one, I hope you can see both pieces at the same time. So you see I go from G1, 0, 0Q to G2, 0, 0Q. And now it's already more complicated. As zeta goes to 0, I also pick up a logarithm. Well, I also have these entire terms on the right-hand side, the 1 plus order zeta. But here I get the first logarithm. And then this goes on to the end of this first congruence class, so n1, where I also have the n1 minus first power of a logarithm, and then lower order terms and so on, all the way down to no logarithm. So this is a way of representing the n1 linearly independent solution coming from the first congruence class. So once again, all terms 1 plus order zeta are analytic at 0, so there's no issue there. So at this point, some of these can still be expressed in terms of hypergeometric, generalized hypergeometric functions, but if I do this all the time, I end up with way over 40 pages, so I decided I will focus on Meyer's G function only from this point on. So here's a first result. And you see, we still haven't talked about Euler, so we'll get there, of course. But at the moment, we are just looking at the simplified differential equation 3 star, and I think I have it on the next page. Yes. So just to remind you what I'm talking about, this is the simplified G function differential equation where P and N are equal to 0. And so let's go back to the beginning of this result. So here's then, this is a summary now, a fundamental system of solutions. So you start with G1 all the way down to Gn1, 0, 0Q. So this was the first congruence class, then you go to the next congruence class and so on. And all solutions are expressed now in terms of Meyer's G function, all the way to the last one of this form. So you get various f's, or in this case g's, and in case of f's, you get f's times powers of zeta and powers of logarithms. All right, so this is the differential equation we are solving at the moment. Now let me make the connection to the Euler differential expression. So I'm introducing a symbol now, tau n, for this object on the right-hand side. Just it's convenient. I did this also at the very beginning of this talk. So z to the minus n and then z ddz minus lambda j is my nth Euler differential expression that depends on these parameters, complex parameters, lambda 1 all the way to lambda capital N. And now I'm going to look at the generalized eigenvalue problem, as I promised at the very beginning. So we look at this differential expression on y producing a multiple mu times y. And if you make the following change of variables, so you go from z that you see here in the Euler differential expression to zeta that you see here, and you see it involves the parameter mu, and you divide z by capital N, and then you take it to the nth power. So that's the change from z, or if you want somehow z to the n to zeta, and you introduce a new function y that then depends on zeta. It turns out that eta satisfies the simplified differential equation for the Meyer's G function, where you have two zeros here. So n is 0, and once again, p is 0. So that is the connection between all these Meijer differential equations and the generalized eigenvalue differential equation for Euler. So that's the fundamental connection here. So that's the reason why we had to discuss Meyer's G function. And so I can now combine the result we just had, so theorem A if you want, with getting a fundamental system of solutions for Euler's differential equation. So how does this work? Well, let's first look at the generic case. Now, in this situation, the b's are lambda j's divided by n. You can see this here. We have 0, 0, so there are no a's, so to speak. And in this particular case, if one is in the generic case, so that these differences of parameters, these b parameters as we called them earlier, if their difference is not an integer, then not much happens. You get powers of zeta with exactly the b, so lambda j over n, multiplied by generalized hypergeometric functions. And that's your fundamental system of solutions. So this is the generic case. So you see the differential equation was of order n. We can go back to that for a second. Here it is again. This is the differential equation, the Euler eigenvalue differential equation if you want. Here's our differential operator, differential expression to be more precise, regarding Euler. And here is, in the generic case, a fundamental system of solutions in terms of just generalized hypergeometric functions. So you would not need Meijer for that. However, if you... So this is another way of expressing what I just said. So when you write this in terms of y as a function of z, so now we are talking Euler itself, you get you make this variable transformation. You can see the part of it here, and you get I mean here in particular you see the variable transformation. So that is now a fundamental system of solutions for the generalized Euler eigenvalue problem. So once again, tau n being applied on y, giving a multiple mu times y. Now, this is subject to plus, and plus here is the generic condition for the b's, or in this case, the lambdas divided by capital N. All right, that's just a generic case. So let me give an example. How about n equals 1, which is automatically generic? In this case, the answer is very simple, as one expects, of course. So this is your differential expression when n is 1. And if you look at the Euler eigenvalue equation for this n equals 1 case, well, this is your answer in terms of the Meyer's G function. This is the answer in terms of generalized hypergeometric, but in this particular case, you get 0, 0, and so it's just an exponential. So that is, of course, no surprise. This is a first-order differential equation that one solves in calculus 1. Already the case n equals 2, as you will see, I have an example for that also, is quite a bit more involved. I leave you in suspense for that for a little while. And so we go to the non-generic case. All right. So now this condition, this was the generic condition, will be violated. So once again, we do our congruence classes modulo the integers. And I repeat what I did before. So this was the simplest one that we looked at. And in this case, we know that in this particular case, when n and p are 0, we get our simplified Euler differential equation 3 star. So here it is once more. Now, what I really want to do is I want to solve the corresponding Euler generalized eigenvalue differential equation. And in order to do that, I'll go back to Meyer's G function and this variable transformation that I showed you a little earlier. And in this case, here's what we get. So a fundamental system of solutions of the general nth order simplified G function dE3 star is, I repeat something we had seen already before, is given in terms of these G functions. So I now only write down G functions and no longer write Fs, even though I could write Fs in some cases. And again, you go through all the congruence classes. Here's my first one. Then you go on all the way to the last one. And you remember the replacement where zeta went into a power, the nth power, in fact, of z, so that you go from Meyer's simplified differential equation to the eigenvalue equation for the nth Euler problem. And again, mu is the spectral parameter here. And so here, with this substitution, you get the solution of the fundamental system of solutions for this object, also in the non-generic case. Now, rather than giving you the summary of this again in terms of the solution for Euler, let me give you the n equals 2 example next. Okay, so you see, we have two parameters, lambda 1 and lambda 2, and we want to solve this differential equation. Now, you will see that this time the solution is a little more complicated than exponentials, as we had in the n equals 1 case. In fact, you will need Bessel functions for this. And to get to that, so this is my abbreviation of the regular and irregular modified Bessel function of order nu, and they will show up very quickly. So in the generic case, so when the difference of the lambdas, we have only 2 here, is not an integer, well, we get I of lambda 1 minus lambda 2 over 2, and then I of minus that expression. You see, it's lambda 2 minus lambda 1, and it's well known that these two functions are linearly independent as long as the subscript here is not an integer, which is exactly our generic condition here. Now, in the non-generic case, this doesn't work. In the non-generic case, these two functions would be proportional, and so we have only one solution. Sure enough, if I'm in the non-generic case, so if the difference of lambda 1 over 2 minus lambda 2 over 2 is an integer, then I get still this solution, which is now one and the same, up to constant multiples. And the second solution, you have to use the modified irregular Bessel function of index lambda 1 minus lambda 2 over 2. So this is the explicit case for capital N being 2. And I see I have a few minutes left, so I can very briefly talk about the non-homogeneous nth-order Euler differential equation. And homogeneous here means that I have a right-hand side. So this is not homogeneous in X or Z. So what we do is, for convenience, because tau contains the factor z to the minus n in front, I multiply my non-homogeneous term, let's say capital F of z, by z to the minus n and then times little f of z. So this is just for convenience that I represent the right-hand side in terms of a power times a non-homogeneous function f on the right-hand side. Sorry, a non-homogeneity term on the right-hand side. So again, what you do is you look into groupings of pairwise distinct elements. You count multiplicities, and so this is what's done here. And as a result, you get a solution of the now non-homogeneous in this sense that the right-hand side is non-zero, nth order Euler differential equation is given in the following way. You have linear combinations of powers and logarithms, and then you get, so this is what you would get from the homogeneous term, and this is what you get from the right-hand side when f is non-zero. So you have repeated integrals, so you have parameter integrals S1 to Sn and powers and f of this argument. So one can show that this is the solution of this non-homogeneous Euler, nth-order Euler differential equation. I should mention that the special case n equals 2, we just looked at this in the homogeneous situation where the right-hand side was 0, and we got Bessel functions as solutions. The very special case n equals 2 is indeed well known and can be found in Inz's book on ordinary differential equations on page 202. So this concludes my talk, and let me just mention a little what this is based on. So we have done a half-line homogeneous, and homogeneous now with respect to X, essential self-adjointness questions, jointly also with Gerald Teschel. We looked at problems like this, not only the second-order case, but that was the main part in a particular paper with Markus Hunziker. And what I was just talking about now is based on a paper on Meier's G function and Euler's differential equation revisited. Thank you very much.
Thank you very much for the very interesting talk, Fritz. And now it's time for questions, please. Meanwhile, may I ask you first, is there a relation of these results with the islands of non-self-adjointness you mentioned?
Okay, so the islands of non-self-adjointness come implicitly by analyzing zeros of certain polynomials. So the zero structure of certain polynomials. And the zero structure is relatively simple when m is 1, 2, and 3. We don't know for sure for 4, but we know for m equals 1, 2, and 3, there are no islands. So you get a half line for the essential self-adjointness situation. But again, when m is 5 and the dimension is 20, the polynomials we had to analyze show that there is indeed, there is 2 intervals then. So a compact interval 0 to alpha, where you are essentially self-adjoint, and another half line beta to infinity, and alpha is strictly less than beta. So there is an interval, the open interval alpha beta, where you are not essentially self-adjoint. So it's a subtle result that depends on the geometry of polynomials.
Okay, thank you. And another question: if Probably you know if there exists some results on the transformation operators which allow to transform this Euler's equation without a potential, let's say, into the equation with a potential.
So I know that you're very interested in transformation operators. I don't know much about what this means in this particular context. I have to say. So it's not something we used. So
Yeah,
our thing was really analyzing the underlying sequence of ODE operators. Once you do an angular momentum decomposition, then you get ODE operators, and in this particular case, some of these ODE operators relate to Euler's generalized eigenvalue problem, right? So this is how we got to it. But I don't know, this is the honest answer, what would happen if we apply the transformation operator machinery to this. I don't know.
Okay, thank you. So please, more questions. It was indeed quite clear, in fact, your lecture. Of course, many details.
I was hiding
but,
all the ugly parts.
yeah, I understand. But
I first, when I wrote this talk for the very first time, it was probably about 45 pages. Then I had a lot more details, but I figured that's impossible. So I have to focus on the G's only in the end and all that. So yeah, now the details are not that simple. I mean, they are involved. And surprisingly, I mean, I always, when I give a talk like this, I'm a little afraid that somebody in the audience knows a particular book where this non-generic situation has been discussed, because we had to develop it. We could not find it. Let's put it that way. So we developed a non-generic case that I described ourselves. So the standard books on this subject, whether it's Magnus Oberhettinger and so on, you cannot find these results in there. At least we couldn't. And I'm still a little surprised by this, because you would think the Euler equation is such a well-studied object, but apparently not the eigenvalue, the underlying eigenvalue equation. So that was a big surprise to us. And I mean, we would have never had the idea to study this had we not been led to it because of the essential self-adjointness problems. They naturally lead to this eigenvalue differential equation.
So thank you very much again, Fritz, for accepting this invitation and for the very interesting talk indeed. Thank you.
Thank you very much.
Thank you very much.